In our previous lesson, we calculated the sum for a finite geometric series where there was a limited number of terms. We're now going to look at how to calculate the sum for an infinite geometric series where there is no last term. So we're going to start with an investigation here. We know that we can determine any term using this formula in a geometric sequence. So I'm just going to start making a table of values and listing out, let's say n is 1, 2, 3, 4. Remember, n has to be a natural number, so 1 is the first number that we can choose. We're going to substitute into the formula and we're going to get the value of each term. So to make this simple, let's just say term 1 has a value of 1 and I'm going to choose a common ratio of 1/2. So if I substitute n is 1, 1 minus 1 is 0. Anything to the power of 0 is just 1. So 1 times 1 gives me my first value of 1, and then we can plot this. So on my x-axis we have the term number, on my y-axis we have the value of that term. So our first term has a value of 1. If I put a 2 in for n, so 2 minus 1 is 1, 1/2 to the power of 1 is 1/2, times 1 is 1/2. So when I have my second term, will have a value of 1/2. My third term, 3 minus 1 is 2, 1/2 to the power of 2 is 1/4. So my third term has a value of 1/4, and we're going to continue on. So you can see that as the term numbers get larger, the value of each term is getting smaller. So this is approaching 0. Is there a number we can put in here for n that will give me an exponent that we can somehow get 0 as the term number or get a negative term? You can grab your calculator and play around here, but you're going to discover that there isn't. Sometimes if you put a really large exponent into this particular example, your calculator will round to 0, but in this case, we're never actually going to get a value of 0. We're never going to get a negative value. So as n is getting larger, the value of each term is getting smaller and smaller and smaller. So we are approaching 0. Let's now try this again, but this time we're going to use 2 for a common ratio, and I'm going to keep my term 1 as 1 just to make it simple. So n is 1. 1 minus 1 is 0, so we put 0 here. Anything to the power of 0 is 1, times 1, my first term is 1. n is 2, 2 minus 1 is 1, 2 to the power of 1 is 2, times 1 is 2. So again, we can go along here, and this time as n is getting larger, you can see that the value of each term is getting larger and larger and larger. I shrunk this down here and put them side by side so that we can compare them. But what you're going to notice is that if our common ratio is between -1 and +1, as the term number gets larger, the value of that term is getting smaller and smaller and smaller and smaller as we go along here. So what we can do is actually start to add these all up. So 1 plus 1/2 is 1.5, plus another quarter, 1.75, plus another 1/8. And you're going to see that as we add smaller and smaller pieces, we are approaching a sum of 2. If we have a common ratio that is outside of this range, so if r is less than -1 or greater than +1, we're going to end up with terms that get increasingly larger where they're not approaching that fixed value, and we're not going to be able to determine the sum. If our common ratio is between -1 and +1, we have what's called a convergent series. As the number of terms increases, the value of that term is getting smaller and smaller and smaller. We're approaching 0, so we can actually add all of those terms up and get the sum of that series, because we're taking this value plus this value plus this value plus this value plus this value, and then all these little pieces here are so small that we can approximate the sum. Recall the formula that we used to calculate the sum of a finite geometric series, and we now know that r to the power of n in an infinite geometric series, if we have a ratio within that range, is going to approach 0. So we can even see this. So I have a common ratio of 1/2. As those values of n get larger, we are getting closer and closer to 0. So as this is becoming 0, what we're left with is the sum of an infinite series can be found by just taking that term 1 and dividing by 1 minus the common ratio. Remember, r cannot equal 1. That would make the denominator 1, and we would then have something that's undefined. If we have a common ratio that is less than -1 or greater than +1, we have a divergent series. So now we can see that as the terms go along here, the value of each term is getting increasingly larger. We're not going to be able to calculate the sum for that particular series, so we would just say if it's an infinite series with a common ratio within that range, we do not have a sum that we can calculate. So if we have a series and it is an infinite series, it keeps going, we're not told told that we have to calculate so many terms in that series, the first thing we need to do is check the common ratio. So I can see that in my first case, the common ratio is -1/3. If it is between -1 and +1, we can find the sum. The value of all of those terms together will approach a certain value. So we're going to substitute into the formula. My first term has a value of 1, so we can put that in there. My common ratio is that -1/3, which we can substitute in here. And then we can go ahead and simplify. Remember, a negative times a negative is a positive. We need a common denominator, so 3/3 plus 1/3 gives us 4/3, or 4/3. And then when we divide fractions, we're multiplying by the reciprocal. So we have 1 times 3/4 when we flip that over, which is just a sum of 3/4. So all of these terms here, as we continue on, will approach a sum of 3/4. In our second example, the common ratio is -2. -2 is outside of that range, so we have a divergent series. We cannot calculate the sum on a divergent series. Every repeating decimal can be thought of as an infinite geometric series. So if I take this 0.584 repeating, I'm just going to write it out like this as opposed to the bar notation. And then we're taking each group of repeating decimals, and I can write them as fractions. So this 0.584, that's 584 thousandths. This next group is going to be 584 over 1 million. This next group, 584 over 1 billion. And that process is going to keep going. And then we can also see that we're multiplying each fraction by a common ratio in order to get to the next fraction. So I'm going to take one of those fractions, divide the one before it. And so these two might be the easiest to work with. So I'm going to take this fraction, I'm going to divide it by this one. And so we're going to change division to multiplication, reciprocate that second fraction. And then we can see that 584 will cancel with 584, and 1,000 will cancel with those digits, leaving us with the common ratio of 1/1000th. So now what we can do is take our formula, because this will continue to infinity. This common ratio is between -1 and +1. So term 1 is that 584 thousandths over 1 minus our common ratio. So we need a common denominator here, and I can see that it's going to be 1,000. So mentally, I know I have 1,000 over 1,000. So 1,000 minus 1 will give me 999. The denominator is going to stay the same. And then this division changes to multiplication. I'm going to reciprocate that denominator, and we're going to end up with this. The 1,000ths will cancel, and that leaves us with 584 over 999. You know that this is a repeating decimal equivalent to this. The last thing we're asked to do here is to determine what are the values of x that will make this particular series convergent. Now we know that it's convergent if that common ratio is between -1 and +1. So we first need to figure out what is this common ratio, and we can take any term and divide it by the term before it. We can take any two terms, but let's go with these two. So 3x divided by 2 divided by 3. Remember, we're changing division to multiplication, reciprocating that second fraction. My 3's will cancel out, and then we have x times 1 is just x, and we have 2 on the denominator. So I know that if my series is going to be convergent, the ratio, which is x over 2, has to be between -1 and +1. So we need to figure out what are the values of x. So I need to get x isolated. Right now I'm dividing by 2. If I multiply by 2, we know that 2 halves will cancel out, leaving us with 1x. And then to keep everything equivalent, I need to multiply every term by the same value. -1 times 2 is -2. 1 times 2 is +2. So in order for this series to be convergent, my x value has to be between -2 and +2.